So thank you for being here. So I'm with the National Research Council Canada. I showed the slides are not up to date, so I'm also affiliated with Université de Montréal as an adjunct. This is joint work with Frédéric Dupuis and Louis Salvaille, also both from Université de Montréal. So my talk will be about Fiat-Shamir for proof in the presence of shared entanglement. So I'm sure you all know what shared entanglement means. So I will go quickly over that part and spend some time explaining the other notion of proofs and the Fiat-Shamir transform. So in our scenario, we're interested in interactive proofs. So we have a prover on the left that tries to convince a verifier on the right that a statement is true. So this statement could be that X belongs to some language L. L could be an NP hard language such as 3SAT, for example. And we're going to consider a special family of interactive proofs that are called Sigma protocols. In this interaction, the prover begins by committing to some information, sends a commitment A. The verifier sends a random challenge to the prover, and the prover should respond to this challenge. And the verifier would either accept or reject based on the information that it has. We are going to ask the following properties of our protocols. Public coin, so the challenges are uniformly distributed. Special soundness, so soundness is just that it's not possible to prove false statement, and we will consider a stronger notion of soundness where for any false statement, there is only a single challenge that can be answered correctly. And finally, correctness, if the statement is true, then the verifier should accept. We do not care about zero knowledge in this talk, so I do not present it. All right. So interaction is costly. So you have delays and you send messages back and forth. So ideally, we would want to prove things non-interactively. So a way to do this is using the Fiat-Shamir transform. It's a very generic transform that takes any such public coin protocols and turns it into a non-interactive proof. And the way it works is that the prover will use a hash function h and will apply this hash function to its commitment A to compute the challenge of the verifier. And then, so the prover has the commitment, has the challenge, so it can compute the response and just send the whole transcript to the verifier. So when does this give us a sound proof? So this hash function should produce a challenge that is uniformly random and independent of this commitment A. So we want basically to mimic the interactive setting with this non-interactive setting. And one very such nice thing of the Fiat-Shamir transform is we want it to be universal. We want it to preserve the soundness of every interactive proof, every Sigma protocol. So one hash function that satisfies all of these nice properties is the random oracle. So the random oracle, you just pick a completely uniform hash function at random, and then the prover and the verifier can both query the random oracle at the point A, get back h of A, and so everything was fine. So this random oracle, you can instantiate it using a trusted party, where if you give it an input A, it will sample h of A at random and return this value, and then put that in a table and give back the same value when it's queried on the same input. Unfortunately, the random oracle is not a physical object. It's not something that exists that you can instantiate without a trusted party. So in practice, we rely on other models to try to achieve this Fiat-Shamir transform. One such model is the common reference string model, where both parties share, they both receive some string S that is taken from some distribution, and then the hash function is computed using S as well as A. Unfortunately, this common reference string model does not, in general, preserve security of the Fiat-Shamir transform. So a brief history of the soundness of Fiat-Shamir. We know it preserves soundness in the ROM and QROM. So even if the adversary can quantumly query this random oracle, soundness is preserved. For the CRS model, the common reference string, mostly negative results are known. So we've known since, also I don't have the dates, but I think it's early 2000, that for argument systems, so proofs that are only sound against polynomially bounded provers, there are, for any hash function, there's a proof that is not sound when you Fiat-Shamir transform it. And the same holds for proof, even against, even for proofs that are secure against unbounded provers. There are, for any hash function, there's a proof system that is unsound when you apply the Fiat-Shamir transform. And I should note that there are positive results for the Fiat-Shamir transform. We know how to preserve soundness in some cases, but it's not a universal transform. So it doesn't preserve soundness of all interactive proofs. So like the hash function and the CRS needs to be tailored for a specific protocol. So in this presentation, we ask the question, can we have a universal Fiat-Shamir transform in the quantum world? And so why do we even think that this is possible? So the title should have hinted a bit at the reason, is that in a quantum setting, we can have entanglement. And if you have pre-shared entanglement, you can do the following thing. So let's say now I've kind of transposed the whole picture. So I have the prover on the top and the verifier on the bottom. The prover will measure its part of the EPR pairs in some basis A, will get a uniformly distributed outcome C. And it can use A as its commitment to choose the measurement and C as the challenge for the verifier. And then the verifier, when it measures using the same basis, will get a correlated outcome. So this is very Oracle-like, right? So you have the uniformity of the outcome. And moreover, if you choose your family of bases carefully, you have some sort of independence where the outcome in one basis, A, doesn't tell you anything about what would have been the outcome in a different basis, A prime. So we investigate the possibility of doing some sort of random oracle using quantum entanglement. So this motivates the following model, which we call the common reference quantum state model. If you were here on Monday, you've seen something similar in the talk of James Bartusek, where they use this to make oblivious transfers. And so in this model, they both receive some entangled state. I don't assume that it's an EPR pair, it could be anything. And the prover will perform some measurement on its part to get the challenge. The verifier will make a corresponding measurement to verify the challenge. And then this ideally will lead into some sort of interactive proof, non-interactive proof. So we capture this thing that we're trying to do as a cryptographic primitive. So we call this a weak one time because you measure, you destroy, random oracle. And so I've just taken the picture from 2 slides ago and just put a box around it and call this a Wartrow. And so we call it weak because the only thing that we ask, we don't want necessarily to have uniform randomness as outcome. We just want that the outcome is not a deterministic function of the input, of the measurement that you apply. And it's not too hard to show that this is sufficient to do Fiat-Shamir because you sort of avoid this bad challenge function that you have for a special sound protocol. Okay, so this is all I'm going to say about Fiat-Shamir for now, is that we're going to try to achieve this weak one-time random oracle because in particular it implies Fiat-Shamir. So unfortunately, maybe fortunately, I don't know. We show that it's not possible in general to have a Wartrow protocol even if you share entanglement. And so our proof is that basically for any such protocol, we will construct an attacker. So let's say you have a Rocho protocol, a weak one-time random oracle. So you have some shared entanglement in a state psi, and then the adversary will take the place of the prover, and its goal will be to produce an outcome A and a challenge C that will be equal to f of A. So remember, we're trying to avoid functions of the input as the output. So the attacker will produce an output that is a function of the input. So the attacker, so the first thing that it does is it's going to select a function at random. So this is the function it's going to hit. The attacker will be using the POVM operator of the honest prover. So so n is going to be the POVM of the honest prover in the protocol. So I just assume that there is a protocol, and this attacker will be using the protocol to cheat. And its goal using the POVM will be to get the outcome that corresponds to so n is the POVMs for any A that defines a POVM. So the sum over C of these things is the identity. And so the goal of the adversary will be to observe the POVM element that corresponds to f of A when it puts A as, when it selects the measurement NA. Okay, how can it accomplish that? So basically, we use the operator Chernoff bound of Alsved and Winter to show that these operators NAF of A, when F is selected at random, they are operator valued random variables. And their expected value, we can compute it as some scalar times the identity. And if you sum these operators over, or if you take the average over A of these operators, then the Chernoff bound tells us that it shouldn't exceed by too much its expected value. So so this is an ordering of operators, and so with overwhelming probability, this upper bounds the sum operators. And if we take the scalar on the right-hand side and divide it on the left-hand side, we get that we have a sum of operators for over A that are at most the identity. So this means that this almost forms a POVM measurement. So if I sum all of these operators, with overwhelming probability, I'm less than the identity, so I can just add the difference, and this gives me a measurement. And one important thing to note is that this success probability is overwhelming in the difference between the input size and the output size. So if my measurement has a smaller outcome than the number of measurements that I apply, this attack is going to work. Great. So this attacker is inefficient. So it hits a random function. So just storing a random function in memory is inefficient. And but what about computational security? So can we have a computationally secure virtual based on a computational assumption, such as learning with errors? We also have a negative result for the computational security setting. It is what we call a black box impossibility result. And the technical statement is that you cannot have a proof that uses a fully black box reduction to a cryptographic game. So if I give you an adversary against Watro, you cannot have a proof that uses a black box reduction fully to a cryptographic game. So those that were here yesterday and have seen Yael Kalai's talk, you are quite familiar with black box reductions now. And so let me just go briefly as a recap. So basically a cryptographic game is just a standard assumption, right? So you have a challenger that interacts with an adversary, and the adversary either wins or not the game. And well, I mean, there are So there's a probability with the winning probability. So you can have either p equals to 0 for search games, p equals to 1/2 for distinguishing games. And so black box reduction. So the reduction, if there were a reduction from a virtual adversary to a crypto game, the reduction would look like this. So the reduction has black box access to this adversary. The adversary receives a quantum register from the shared EPR pairs, the shared entangled state, and produces a classical outcome that it sends to the verifier. And so this is the interface that the adversary has access to for this this adversary. And so a reduction from virtual to a cryptographic game would be a reduction of this form that wins the game if A is an adversary for virtual. So how do we prove such an impossibility result? Well, basically, we show that the adversary can be simulated. So the adversary is inefficient, but there is an efficient simulator that can produce something indistinguishable from the adversary. So if the reduction wins with the adversary at this cryptographic game, then the reduction also should win with the simulator, since they are, in this case, statistically indistinguishable. But this reduction plus the simulator is an efficient algorithm because the simulator is efficient. So this basically breaks the game. This means either the game is not secure or the reduction does not exist. So I will just briefly mention that we have other results in which I didn't have time to go through in the paper. So this is the impossibility of Wautreau, but we can use the same techniques for impossibility of Fiat-Shamir. There's a slight difference between both primitives. And right, so I will let you have a look at this slide. So this is the end of my talk. And so I will leave this slide on in case you're interested. Thank you.
Thank you, Philippe. Do we have any questions? So I guess maybe, do you have any future work that you're interested in from like these negative results?
So one of the interpretation of this negative result, right, is that it tells you which path you should not take to try to prove security. So one of the contribution in the paper is to use a non-game assumption, like assumption about quantum adversaries, but you cannot frame it as a game with a challenger. And you know, classically, you can do Fiat-Shamir on some sub-exponential hardness assumption. So maybe you can do something similar with a quantum setup, but using lesser assumption. That would be potential areas of future research.
Could I ask a question? Hi, yeah, thanks. So could you, I might have missed this, but could you say a couple words for how in your last result that you mentioned, showing the possibility of black box reductions, how you construct the simulator to show this?
Yeah, so basically, so it's very similar to the classical setting. So classically, the impossibility result, there's the same sort of statement, and this is kind of the techniques are similar, but we port them to the quantum setting. So the adversary hits a random function. So its output is completely random, and from the reductions point of view, it's also independent from the input. So basically, the simulator just samples random bits, takes that as output, and just keeps track of well, quantumly, we don't need to keep track of which questions were asked because they're random themselves. But classically, like it's kind of lazy sampling for a random oracle. It's the same strategy essentially.
Thank you, Philippe. Any other questions can be taken offline. So let's thank Philippe again, and we can set up the next talk.